So hopefully along those lines, I'd like to be doing sort of a contextual thought, which places both bits of research together. What is an engineer's perspective of mathematics? And I would like to think that, and maybe you'd like to disagree, but an engineer really is interested in how maths can become a tool for them to perform a certain function. They're not really interested in the beauty necessarily of mathematics, they'd like it to serve a purpose. And so this is effectively what we're trying to do. So we're mathematicians, but we'd like to be able to provide a design tool for engineers. And what we're looking at is how would one create a mathematical design tool so that you can go away and create free-form motions. For example, if you want to design the motion of a robot arm, or if you're doing some sort of machining, how do I do that? What's the mathematical tools to do that? So my proposal is I'll go through the overview of how one may create these motions as a design tool, and I'll give you sort of a recipe of them unlike mathematics, but I won't go too much into detail. Of course, if you're really keen, you can go through the paper and they'll be in there. But effectively, how do we go about doing this? We're going to take some inspiration from curve design. Now, if you think about how a curve works, especially if you've got a parametric curve, effectively, as you move the parameter, your point moves in space, and so we can think about a curve as a moving point. So that's very similar to a motion. So with a motion, we've got a body that's moving. So as the body moves, not only is it moving in space in terms of translating or changing its position, it's also changing in orientation. And we can think about this as a rigid body transform that's changing across our parameter. And so how can we design a motion using these ideas? So the outline for the talk is we're just going to briefly look over curve theory to see how curves are constructed, and then we should hopefully perform some analogies with motions, and so we can look at how we can apply the same ideas to create motions that might be useful for things like cutter tool paths. And in order to do that, we're going to have to introduce this flavour of mathematics called geometric algebra. So hopefully that won't be too intimidating, but we can go skin quite past it. And then from that, we have developed different types of motions that we can use, and the ones that we think are better than the others, and then we'll finish with some applications and some conclusions. Okay, think about free-form curves. Perhaps the most familiar curve design tool is the Bezier and B-spline forms. So hopefully many of you are familiar with these. So to begin with, we're going to look at the Bezier form, and we will revisit the B-spline later, because they're very, very similar in nature. So if I have a Bezier curve, in this case we're going to have a cubic Bezier, we have 4 control points, and from those 4 control points I want to generate a curve. So what's the process that we do this? So one way to generate this curve is to use a process called the D'Agasio algorithm. And the way the D'Agasio algorithm works is, in between the consecutive control points, we connect them with a straight line, and then depending upon which parameter value we're looking for, i.e. how far a point along the curve, we then travel along that particular line a certain amount. So in this case, we're traveling about 2/3 along the line, and then from that we get a point. We do that for all consecutive pairs, and then the next step of the D'Agasio algorithm takes these points, connects them again with a set of lines, finds some points on those lines, and then, as you can probably predict, the final step is to connect those 2 last points together with a straight line again, and then find the point on that line. And we do that for all the different parameters, and we sketch out the curve. So that's the basic construction for a free-form curve. And the important thing to remember is we have some control points, and from those control points, we combine them in pairs repeatedly until we finish, and then we get a point on the curve. So the question now is, can we do the same thing with motions? Yeah, of course we can. So let's go through that sort of process. But before we do that, we need to think about how do we represent 3D transforms. So with a transform, we need to think about a translation and a rotation, so we can't really use vectors. And perhaps the most common approach that you'll probably be familiar with is perhaps you can think about it as using transformation matrices, so perhaps a rotation matrix or similar. However, these provide some issues when we look at the underlying maths. So one problem that we have is if we take 2 rotation matrices and we add them together, what what we end up with isn't necessarily a rotation matrix. So we have to do some fiddling around. However, there is an alternative, and that's to use something called geometric algebra. And these help us to define our transforms in a more robust manner. Why are we using geometric algebra? Well, it allows us to describe geometry really well, first of all, but within there is a way to generate these rigid transforms that we're after, which are going to help define our motion. And it's all wrapped within a single framework, whereas with matrices it's a bit more complicated than that. Now, you probably have another question, which is, what exactly is a geometric algebra? Now, think about a standard vector space. With a vector space, you have a set of basis vectors, and then you can sort of combine them together using addition and do lots of fancy things with it. With a geometric algebra, the extra facet is that now we can multiply vectors together. If we're going to multiply vectors together, we have to give some rules. So here are some rules for multiplication. Now, don't worry too much about the semantics, it's just for completeness, but effectively what we have is, if we multiply two vectors together, if we swap the order of that multiplication, then the thing becomes a negative, so we call this anti-commutativity. That's one of the math rules. And also, if one of the basis vectors happens to multiply itself, then that thing disappears and we're left with a scalar, either a 0 or 1. So if we think about what that means, when we create a geometric algebra and we keep multiplying all the things together, we're going to get various combinations of our basis vectors, and these are going to be objects in the space. And if an object has a certain number of subscripts, so it's a combination of a certain number of these basis elements, we're going to say that has a certain grade, equal to the number of subscripts. And we also have something that we're going to do with them called reverse. So this is sort of like complex conjugation, and what a reverse will do is it will take that geometric element and it will just reverse the order of those subscripts. So this is sort of like the recipe to begin with. What do we need? What's that useful for? So let's say I want to represent a point. Well, this works in the same way as we're used to for vector spaces. So a point has a representation where we effectively put the x, y, and z values in front of our standard vectors, if you like. And if we want to be a bit fancy, we can also do a homogeneous model using the fourth coordinate. But the thing that we're really interested in here is how we're going to perform a rigid body transform. So how it happens is if you take any even grade element, and so by that I mean any geometric algebra, anything in the geometric algebra, which when you measure the grade by the number of subscripts, happens to be an even number, then this will actually correspond to a rigid body transform using this map here. Okay, so what that means is, when I'm thinking about a rigid body transform, what I think is I can represent that not with a matrix now, but with this thing called an even grade element, which perhaps if you want to think about it practically, it's just a list of 8 numbers, sort of like 8 coordinates, if you like. So just to give you an example of what's going on, here we have an example of an even grade element up here, and what this thing does is it's going to rotate whatever object I'm looking at in the z-axis by an angle theta. So those of you who are familiar with Euler's identity in complex numbers,
addition theorems.
So you see this thing here looks a bit like I. So if you do e to the I theta, you'll get cosine theta plus sine theta I. So this is one of the things that comes out. So what we have here is a way to perform rotation. I don't know if you've ever tried to do rotation with complex numbers, but that's exactly what's going on here. And so here we have an example, a graphical image. I've got this red L-shaped block, and what I do is I apply this transform, which is an even grade element, and it's going to take this L and it's going to rotate it around 120 degrees. We can also do translation. So what we're going to do here is we're going to take our block and we're going to translate it some amount. That is, again, another even grade element. So this is the recipe, if you like, to construct a translation. And now we have an example. What we're going to do is we're going to take the L-shaped block, we're going to lift it 2 units in Z, and so that's what we have graphically here is that translation occurring. And of course we can do a combination of these two things. So what we're going to do now is we're going to take that object, we're going to first rotate it, and then we're going to translate it up. And then to do that, it's rather simple. All we're going to do is we're going to say, right, first rotate, and then translate. So you'll see that we're multiplying the two things together. So now what we're thinking about is we're associating any rigid body transform with this even rate element. And if we think about this even rate element as a function of a parameter, as I change the parameter, the even rate element changes, i.e. as I change the parameter, the transform is changing, and thus I can create a motion from it. So the idea now is how do we define our S of t so that we can generate the motion that we're after. To give you an example, here we've defined S of t, which is a function. So here the even rate element is changing, and we're going to start, and as the thing changes, you'll see it move. You can't quite see it move in 2D, but you get the idea. What we do is we start off with the definition, and then from that we get an idea for motion. And this can be useful in things like defining toolpath motion. So here we have an example of we want to move a tool in a straight line. We can describe that using geometric algebra, or if we want to make the tool go around in a circular shape, again we can do that. And it also allows us to do slightly more exotic toolpath motions. So here we also have the toolpath changing its orientation, and this is useful for things for putting with 4 and 5 axis CNC machines. Now here we come into the first sort of bit of theory, if you like. Let's now recall how we created our freeform curves. If you remember, what we were doing was we were taking pairwise combinations of control points, and then from those control points we were finding a point in the middle. Now, one can write this expression down mathematically and say, okay, we're going to take a linear combination between these two things here, and we get a function that looks very much similar to the second line. However, that doesn't make necessarily if we think about how the geometric algebra is described, and I'll give an explanation. So if we think about what's happening as we change the parameter t along these lines, what's happening is every time we change, it's moving in a constant direction. So if we think about this thing here, every time we're adding a constant change. And so we can think about this as we start off at V0, and we're adding a certain change, and then as we keep adding, this thing here keeps changing depending on the number of steps I take. Whereas with a geometric algebra, we're doing something slightly different. Now we're multiplying things together, and so at every stage as we move along, we need to multiply it by a certain amount. So if I start off with an initial pose, what I'm going to do is I'm going to keep multiplying by a certain amount. And so what that does is it has the effect of saying, actually, the t no longer sits down here, it actually sits in the exponent, which makes the expression look quite simple on the face of it, but having to calculate this thing is a bit of a nightmare, because how do you do things to the power of t? Well, you have to start using things like exponentials and logarithms, you have to start doing the Taylor series, and it gets a bit of a nightmare. So there's sort of like a mix between, so this is, in the literature, the solution that they found to another problem was to have a slightly different representation, which effectively allows you to control the thing inside the exponent. I won't go into too much detail, but think about this as sort of like a sort of an in-between the additive and the multiplicative. And the multiplicative one perhaps seems the most natural, because all we're doing is every step of the way we're providing the same transform, but it's quite difficult to implement on a computer or generate the expressions, because it requires exponentials and logarithm functions. Things don't commute, it gets rather ugly. The additive version is by far the simplest one, because it's sort of just it's analogous to the curve case, and so we have a normal Bezier transform, but there's some issue about what does it mean when you're taking these additive combinations. And then finally the exponential one, that's sort of in between, but again we still need exponential and logarithm. So these are the difficulties when we're trying to do the thing mathematically. However, if we just want to have a look at what's going on here, you can see I have a pair of control poses, and when I do the multiplicative interpolation between the two, I get this thing which follows along the circle here. And if we compare that with the additive case, you'll see that they're very similar. In fact, there's not much difference between them, providing that the components aren't too far apart. And on the bottom, we just have an example of a quadratic Bezier, if you like, defined using a multiplicative way to combine the control poses. And you see we've started to create our first freeform motion down here. And then the final design feature that one might want to have is looking at things like compound motions. So what we mean by this is we're going to have an object to undergo a motion, and then within that object, that thing might be moving within itself. And how would we design the mathematics to accomplish that? Well, we simply multiply one motion on top of the other. So for an example, what I'm going to do is I'm going to take an expression for a motion which is going to rotate n times in the z direction, and then as the thing is now rotating in the z direction, what I'm going to do is I'm going to push it forward along an axis. So here's the picture. I have an arrow up here, or a set of perpendicular arrows, and then what I'm going to do is I'm going to push the arrow along the axis, and as I'm pushing it along, I'm going to spin it. So you see how I'm able to build up these motions using simpler or base motions. And we can create some more interesting motions. So here we have the thing, instead of going in a straight line, we're going to wrap it around a circle. And again, as we go around the circle, we're going to spin it around. And then we have a rather interesting motion that's being constructed. So here what we have is a train that's going to travel along a Möbius strip, and it's an example of a compound motion. What we have to do is we have to get the train, first of all, to be in the correct position, and then once we have it in the correct position, we also then need to orient the thing, and it's a shame we don't have the proper animation, but you can actually see the train going all the way back and then underneath itself, as it were, as it comes back. Oh yes, okay, and so visiting the idea of a Bezier construction, that's probably not really in line with how engineers use curve design. I don't think they move the control points. Instead, what's most likely is they're going to have a set of precision points that they go through, and then they're going to create a B-spline through those points. So if we have a look at B-spline theory, what we discover is that when we're looking for motions in our case, is that we can easily adapt it. Because what would be here in the B-spline theory is we would have a set of points, and then from the points we have some precision poses and some control poses, and we set up a set of linear simultaneous equations and we can solve these. And then this is exactly the same with motion. The only difference is instead of control points we just have control poses. So we can solve that problem which we didn't have before. So here's an example of a motion going through for control poses. This is a B-spline of cubic order. And perhaps a more practical example would be a motion that's going through a set of tool poses. So here we just simply say, I want a motion that goes through all of those tool poses. Give me a B-spline motion that does that. And so here we have that motion rendered at various points. And if we think about combining these two approaches, so we could compare additive with exponential, you'll see that there actually isn't much difference. So this sort of motivates why additive has its advantages that you might want to consider. Anyway, as time is running short, I'll finish with the conclusion. So if we think about motion as a varying rigid body transform, there are different approaches available. Matrices are one, however, we propose that geometric algebra has advantages for creating freeform motions, and this is because essentially it has this extra feature which means that we can now add together these things, whereas with matrices we weren't able to do that. And this works perfectly well because now we can create motions from the same point as how we did curves using the Casio algorithms, and we'll notice that actually one of the main reasons why we've created this additive case is because that multiplicative interpolation doesn't quite work when we go into the higher order. Anyway, I shall finish there. Thank you for making it all the way through to the last talk of the conference. And yes, I'll finish it.
Thank you.